In this video, we'll be looking at a very interesting arrangement of resistors in a given circuit. So yeah, let us just begin. And obviously, to make it more intuitive, I'll be comparing it with my analogy of the water pipe and all, and I hope that makes it clear. So let me take my battery here, and just to compare, I have my pump here, the water pump that lifts the water. Yeah, there you go, the pump. And now if so first of all, I'd like to clarify one thing here before I move further ahead. The pump gives the water some potential energy, so it lifts the water from this level or this height to this height, and in that process it gives the water some potential energy. Similarly, the battery also takes the charge from this end to that end. I'm talking about conventional current again, and in doing so it gives that charge some potential energy, which the charge can then use to perform any work. Now the plain wires that I'm connecting here, the low resistance copper wires that I'm using for connection, is analogous to the parallel pipes because there's no potential drop across these parallel pipes. But now if I have, when I come here I connect the resistor, and analogous to the resistor, similar to the resistor, I can have a pipe that travels from the top from this height down to this height, and all the potential energy of the water is lost as the water travels across from this end to that end of the pipe. And that is similar to what happens at a resistor. When charge flows from this end to that end of the resistor, the charge loses all its potential energy, and the amount of potential energy lost by the charge is equal to the energy it gained here. Now many of you had doubts as to, doesn't the resistor's resistance affect the potential difference? Or the basic query was, so if I have 1 ohm resistor here, even now let's say let me just take some values here. So let's say this is a 3 volt battery, I have a 1 ohm resistor. So if the charge flows and I have a 1 ohm battery, I know that there will be a 3 volt potential drop here. Now instead of taking a small 1 ohm resistor, I take 2 resistors, and let's take large values like 100 ohms and 200 ohms. In this case, some potential drop will occur, as we did in the last video. Some potential drop will occur at this resistor, which will be, I guess, 1 volt, and the remaining potential drop, which should be, I believe, 2 volts, will occur across this resistor. And now the confusion that you people have is that here I have a 100 ohm resistor and still the potential drop is only 1 volts, but in the other case I had only 1 ohm resistor and the potential drop was 3 ohms. How is that even possible? So let me just compare that to this example and clarify this thing here. Let me take a simple 1 ohm resistor. Now a 1 ohm resistor has a very low resistance, which means it does not resist current too much, right? It allows the current to flow pretty much easily because it is low resistance, and therefore the current is pretty high. This is analogous to taking a pipe that is very wide and smooth, which allows the water to flow very quickly, and so a large amount of water flows through the pipe, and that large amount of water, because it flows through the pipe, that is analogous to a high current, right? So the water flows, a large amount of water flows very easily through this pipe because it does not offer any resistance to the flow of water, similar to the 1 ohm resistor, which does not offer any resistance to the flow of current. Now, but if we keep in mind here, the battery gave the charge a potential of 3 volts, and though that potential was lost as the charge traveled from here to here, and the potential drop was 3 volts. That is similar to this case where the pump gave the water some energy, mgh, and as the water traveled from here to here, it makes sense that the water lost all that potential energy. Remember, I'm talking about the potential energy, not the kinetic energy. It lost all the potential energy as it traveled from that point to this point. and yeah, it lost all the potential energy. Now that part is, I hope, clear. The charge lost all the potential drop here. The potential drop occurred here, equal to 3 volts. Now if I take two resistors, yeah, and let's take, this is a 100 ohm resistor and this is a 200 ohm resistor. This is similar to taking let's say this is the first pipe, and let's say I have some parallel pipe. So this parallel pipe is like the small low resistance pipe here, and I have the second part of the pipe. There you go. Right now, the higher resistances of the two resistors is similar to these pipes being very narrow, right? And obviously this analogy is not exactly perfect, so just to fit in everything perfectly, we know that the potential drop across a resistor depends on the resistance of that resistor, right? So this is a larger resistor, this has a larger resistance, so there will be a higher potential drop across this resistor. So just to connect the two cases, I have taken a longer section of pipe to represent this larger resistance and a smaller section of pipe to represent this 100 ohm resistor, right? Now if we observe, even in this case, the potential, so water gains some energy, mgh, just like charge gains some potential 3 volts. Now as it moves here, water loses some potential energy, right, which depends on this height, and that is similar to the charge flowing from here to here in the 100 ohm resistor, and it loses some potential, right? But if you notice here, even though the pipe is much thinner, and water will have a hard time flowing through this, because this will resist the current of this will resist the flow of water, and maybe let's say there's some rocks and pebbles and other things stuck inside the pipe, and the pipe just does not allow water to flow so easily, but still water will flow, and as water goes from here to here, it will still lose a potential energy that is equivalent to this height. So maybe it will be mg times this h1, whatever this height is, and it doesn't matter how bad this pipe is, or even if, rather than taking a straight pipe, even if I have something like this, a very thin pipe just of a very weird shape, even now the drop in the potential energy would be equivalent to mg times this height. So the drop in potential energy of the water does not depend on what type of pipe it is, what the pipe is made up of. Does it allow the flow of water very easily or not? That doesn't really matter. All that matters is the height, that with which the potential drops, right? So if water goes from here to here, it'll face a potential drop of mg times this height, and so that is similar to this case where the resistance does not matter. The resistance will obviously lower the current. So if I have a larger resistance like 100 ohm and 200 ohm, the current will be very low, because that is these two resistors are not allowing the flow of electrons so easily. But even after that, the potential drop across both the resistors will be 3 volts, because just like in this case where I have such weird looking pipes, but again if I have to calculate the drop in potential energy of the water, that will still be mgh, because the change in potential depends only on the starting point, the starting height of water, and the ending height. Similarly here, this point is at zero potential, this is at a potential of 3 volts, and for some charge to move from here to here, even if it moves through 1 ohm resistor or such large resistances, as far as it goes from 3 volts to 0 volts, the change in the potential of that charge is simply 3 minus 0, which is 3 volts, and that is why the drop in potential is 3 volts. I hope I know this is a very weird thing to digest, but yeah, I hope now it makes a little bit more sense than before, and I think I should end the video here, and I'll continue in the next video about the interesting arrangement that I wanted to tell you in this video. But yeah, this video is getting too long, so I'll continue in the next video.